Every voice assistant, every set of live captions, every meeting transcript relies on the same kind of technology, a speech-to-text engine. Its job sounds simple: listen to sound and write down the words, but getting a machine to do that reliably is one of the hardest problems in artificial intelligence. Let's open one up and see how it actually works. Here is the challenge. Sound is just a wave of air pressure, sampled 16,000 times a second. The very same wave can map to completely different sentences. Recognize speech or recognize speech. Speech has no spaces between words. Add accents, background noise, and people who mumble, and you start to see why this is hard. The engine has to turn a messy, continuous signal into clean, discrete text. Almost every engine follows the same 4 stages. First, the raw audio. Second, we turn it into features, a compact picture of the sound. Third, an acoustic model, a neural network that listens. And fourth, a decoder that turns what the network heard into actual words, often with help from a language model. Older systems built these as separate parts. Modern engines learn all 4 at once, end to end. Stage 1, features. We rarely feed raw audio to the network. Instead, a short window about 25 milliseconds wide slides along the signal, stepping forward every 10 milliseconds. At each step, we measure how much energy sits at each frequency. Stack those measurements up and you get a spectrogram, a heat map of sound over time. This is the picture the network actually reads. It wasn't always done this way. For decades, speech recognition was a pipeline of hand-built parts. A hidden Markov model for timing, a Gaussian mixture for sounds, a pronunciation dictionary, and a separate language model, all tuned by experts. It worked, but it was brittle. Then deep learning arrived, and a single neural network trained on enormous datasets began mapping audio straight to text far more accurately. That end-to-end approach is what powers every modern engine. At the heart of the engine is the acoustic model, the encoder. Today, the most popular design is the Conformer, short for Convolution Augmented Transformer. Convolution layers capture local detail, the texture of nearby sounds. Attention layers capture the global context, how a sound relates to the whole utterance. Stack many of these blocks, and the encoder transforms the spectrogram into rich representations of what was said. But now we hit the core puzzle. The audio might be 1,000 tiny frames long, while the text is only a handful of letters. Which frames belong to which letters? Nobody labels that alignment by hand. Solving this mapping from many audio frames to few output tokens is what separates the 3 main families of speech recognition decoders. The first family is CTC, Connectionist Temporal Classification. The idea is clever. Let the network guess a letter for every single frame and add a special blank token for silence or repeats. Then collapse the result, drop the blanks, merge repeats, and what remains is your transcript. CTC is fast and simple. Its weakness is that it scores each frame independently, so it usually leans on a language model to fix spelling. The second family is the RNN-Transducer, or RNN-T. It adds a second network, a predictor, that works like a small built-in language model, guessing what comes next from the words so far. A joiner combines the predictor with the encoder to choose each token. Because it can emit words the moment it hears them, RNN-T is the workhorse behind real-time captions and voice assistants. The third family is the attention-based encoder-decoder. The encoder reads the whole clip, and a decoder writes the text 1 token at a time, attending back to the relevant parts of the audio. This is the design behind OpenAI's Whisper, which was trained on 680,000 hours of weakly labeled web audio. That massive scale made it remarkably robust across accents, noise, and more than 90 languages. There is one more powerful idea: self-supervised pretraining. Models like WAFTVEC 2.0 take vast amounts of audio with no transcripts at all, hide random chunks, and train the network to predict the missing pieces. In doing so, it learns the structure of speech itself. Only then is it fine-tuned on a small labeled set. This is how engines reach high accuracy without needing millions of hand-transcribed hours. So which engines actually use all this? OpenAI's Whisper is the popular open option. NVIDIA's Canary and Parakeet models, released through NeMo, currently top the open accuracy charts. DeepGram's Nova is tuned for low-latency streaming. Assembly A focuses on accuracy plus transcript intelligence. Google, Amazon, and Microsoft offer cloud-scale services. And 11 Labs Scribe pushes multilingual real-time. There is no single best. The right choice depends on accuracy, latency, languages, and whether you self-host. How do we compare them? The standard metric is word error rate, or WER. Line up the model's transcript against the truth and count 3 kinds of mistakes: substitutions, where a word is swapped; deletions, where a word is dropped; and insertions, where a word is added. Add those up, divide by the number of true words, and that's your error rate. Here, 1 substitution and 1 deletion over 5 words gives 40%. Lower is better. But a single number can lie. A model might score beautifully on clean audiobooks and fall apart on a noisy phone call. That's why engines are tested on many datasets: library speech for clean read speech, common voice for crowdsourced accents, FLURS for over 100 languages, and an MI for messy, overlapping meeting audio. Always check the score on data that looks like yours. To compare fairly, the Hugging Face Open ASR Leaderboard averages word error rate across many of these datasets. As of 2026, NVIDIA's Canary model leads at around 5.5%, with IBM's Granite Speech close behind. Strong engines like DeepGram Nova, Whisper, and the latest transcription models from OpenAI follow, all within a few points. Remember, these are averages. On your specific audio, the ranking can change. So let's bring it together. A speech-to-text engine turns audio into a spectrogram, feeds it to a conformer encoder that listens, and uses a decoder, CTC, RNN-T, or attention to produce text. It's trained on huge datasets, sometimes without any labels at all, and measured with word error rate across many benchmarks. That is how machines learn to listen. Thanks for watching.